So we're going to talk about derivative use today. First derivative use, second derivative use, first derivative rule, second derivative rule through 4 examples. And what we're going to find in each problem is intervals of increasing and decreasing, which is determined from the first derivative rule. An increasing function has a positive derivative, a decreasing function has a negative derivative. We're going to find local maxes and mins using the first derivative rule and the second derivative rule. Okay? And again, the first derivative rule says if it goes from decreasing to increasing, there's a minimum, and if it goes increasing to decreasing, there's a maximum. And you can use that along with the second derivative. And if it says if the derivative is 0, that if it's positive, it's a minimum, and if it's 0 and it's negative, it's a maximum for the second derivative rule. Finally, we'll do concavity using the second derivative and find points of inflection. And I thought I'd start off with a really easy function, our favorite odd function, y equals x cubed. And it's a real quick one we can do derivatives of, too. F prime of x equals x squared, 3x squared, and f prime prime of x equals 6x. And what we find here is there is a critical point. A critical point is where the first derivative is either 0 or undefined. It's 0 at 0, so I have a critical point at 0. And here also I have a possible point of inflection. The second derivative equals 0 at 0. So, intervals of increasing and decreasing. I look at the first derivative. I know 0 is a possible point. If I want, I can make a table, f prime of x. And at 0, I know it's 0. And at f prime prime of x, it is also 0. For the first derivative, if it's less than 0, it's positive. And if it's greater than 0, it's positive. So it's increasing on both sides. And we know that. So the intervals of increasing and decreasing on this function is f of x increases from negative infinity to 0 and 0 to positive infinity. There are no decreasing parts, and we know that from knowing what the curve looks like. Likewise, the second derivative is also negative left of 0, because you put in like negative 10, it's negative. You put a positive value in, it's positive. So we know that it is concave down from negative infinity to 0, and we know it's concave up from 0 to infinity. And it changes sign. It's not that the second derivative is 0, that it changes sign across 0. So my point of inflection this time is at 0. If I plug 0 into the original function, it is also 0. And we have now found these. There are no local maxes or mins on this function. There is no sign change on the first derivative. And when the first derivative is equal to 0 for the second derivative rule, the second derivative is also 0. It's not positive or negative. So it is not a local max at 0. Okay? And again, if you use your calculator, you can find this same graph. And I'm not going to graph many of these that we're doing up, but this one's pretty easy for me to just throw a quick graph up. So again, that's what we're going to do in all these problems. We're going to find intervals, max and mins, and concavity and points of inflection. And we're going to do it longhand. No graphing calculators. Alright, next one. Polynomial, continuous. I take some derivatives. I get 6x squared minus 6x minus 12. And I get 12x minus 6. First thing I like to do, and anytime I do these problems, is find the critical points here, find the zeros of each derivative. So, up here, this is a continuous function. It's also, I can see, if I factor out the 6, a factorable polynomial. Now I'm going to end up erasing this for the use of space. So f prime of x is this. Well, obviously this is equal to 0 at 2 and at negative 1. So I have critical points at negative 1 and 2. From inspection, I can set this equal to 0, and I can see f prime prime equals 0 at, how about 1/2? So when I do my charts now, when I think about increasing and decreasing, I'm going to use those 3 values. And again, I'm not going to write out the sections. I'm going to determine the sign in my head as we go. So I have an x value. I have, now maybe I'll leave a column for f of x, f prime, first derivative, and f prime prime. And maybe I'll make a note here of what happens. So, I have -1 space half space 2. I know -1 is a 0 on the first derivative. I know half is a 0 on the second. So again, if I start with finding increasing and decreasing seconds, I look to the left of -1. If I look left of -1 on this function, and I plug in like -100, I see that this function is positive. Likewise, if I look in between -1 and 2, and I plug a value in, I'll see that this value is negative. And if I look to the right of 2, and I put in a big value, 100, into the first derivative now, I'll see it's positive. So I'll see it's increasing here, and decreasing in between. So I can write that up over here. Increasing -infinity to -1, and 2 to positive infinity, decreasing between -1 and 2. Now, I can tell right now with the first derivative rule about -1 and 2. There are sign changes on the first derivative. As you go from left of -1 to the right of -1, it goes positive, increasing, to decreasing. So this is going to be a local max by first derivative rule. Now likewise, if I plug -1 into the second derivative, if it's a local max, I should get a negative number. So if I plug -1 into the second derivative, 12 times -1 is -12 minus 6, -18. Yeah, that makes sense. It's negative. Alright? It is a negative number. And likewise, we're going to find down here that I have negative to positive on the first derivative across 2. Negative to positive. That's a min. But let's do that by the second derivative rule. I'll plug 2 into the second derivative. 12 times 2 is 24, minus 6, 18. That's positive. That means this is a local minimum. Alright, so we can find the mins and maxes by using the original function if you want. So I have a local max at -1. Its value is just by plugging -1 into the original function. -2 minus 3 is -5, -5 plus 12, it's 7. I have a local min at 2, and I can find that value, again, by plugging 2 in. 16 minus 12 is 4, 4 minus, it's -20. And again, I'm awfully fast at that, that's just practice. So I've now found increasing and decreasing. I've found the local max and mins using the first derivative and the second derivative rules. All that's left is concavity and points of inflection. It is concave down, because the second derivative is negative, so it's concave down from -infinity to positive half, and then it's concave up from positive half to infinity. Now, a point of inflection occurs when the second derivative changes sign, not where it's 0. It is 0 here, but it goes negative to positive. So there's a point of inflection at 1/2. There's a sign change. So point of inflection at 1/2. And I'm going to get really lazy here. I could plug 1/2 in here and get the y value, or I could just write this. F of 1/2, right? That's the y value. And then I've found all the information on this graph. So again, there we go. Did the derivatives, found the points of interest, I like to call them critical points, and where the second derivative is 0, and used a little sign table using the function, first and second derivative. Now if I wanted to graph this, I'd probably find the y-intercept and do some curve summary, but right now we're just going to stick to these basics. Alright, so let's put up another function. Maybe you should try it ahead of me. I'm going to go awfully fast on this one, so you need to pause me if you get ahead. Find the derivatives. Now these are just power rule problems. We like polynomials to learn from. Alright? These factor. Both of these factor. Alright? 4x out gives me x squared minus 3. This one factors out to 12. You get x squared minus 1. Alright. difference here, x squared minus 3, x squared minus 1. X squared minus 1 is x plus 1, x minus 1. So I'll tell you there are two places where the second derivative is 0. F prime prime equals 0 at plus or minus 1. I will tell you that up here, we could write this out too. 4x times x plus the square root of 3, x minus the square root of 3. Remember, anytime you have a difference, you can factor it. Anytime. So in this case, I have critical points at 0 and plus or minus the square root of 3. This makes the chart quite a bit more difficult. 1, 2, 3, 4, 5 values to put in the chart. Alright, we'll have a notes section here at the end. Alright, and again, I really don't need this stuff once I put it in the chart. I know negative square root of 3 is negative 1.73, so when I lay out my chart, it is really important that I get it in value order. Alright, so, and again, I have derivative of 0 here, here, and here, and I have second derivative of 0 here and here. Alright, and again, 0 is the easiest one, so maybe I plug in 0 into the original function and find that it goes through the origin as an intercept. And I plug 0 into the second derivative and I find out it's negative. And again, this is a pretty easy function, so if I go to the left of negative 1, I can see that any squared, that this will be positive, and I'll start here and I'll put in like 10 and this is positive. I picked the second derivative because it's just a little easier. Alright? And now I can do my signs in between the zeros here. Alright? I'll try to give myself a little bit of space at the bottom of that square root of 3. A very large negative number obviously is going to be negative here because it's 4x cubed. I'll plug in negative 1. Negative 1 cubed here would be negative 4 plus 12. That's a positive. Becomes 0. I plug in 1. I get a negative, and then I plug in a very large number, and I'm going to get a positive. So I have a whole lot going on here this time. It's changing sign 3 times. So there's going to be 3 maxes or mins here. Likewise, there are 3 different sections of concavity and 2 points of inflection. It changes sign here and here. So now we got to start labeling all this stuff out. So let's start with increasing and decreasing. It is negative here and here. So it's decreasing from negative infinity to negative square root of 3 and between 0 and square root of 3. And these are intervals. Again, increasing then from negative square root of 3 to 0 and from square root of 3 to infinity. Alright. Concavity would probably be the easiest next, but let's do local max and mins. And again, local maxes. First derivative rule says if it goes positive to negative, you have a local max. So let's see if it goes negative to positive. No, positive to negative. How about right here? This is a local max at 0. So at 0, there's a local max. So again, I can plug that into my original function up top, and that is 0. So there's a value of 0 at 0 for a local max. The second derivative rule, alright, or first derivative rule for local mins then says, we'll go back to the second here in a second, local mins go from negative to positive. It goes negative to positive here and here at negative square root of 3 and positive square root of 3. So it has local maxes at negative square root of 3, the x value, and the value here then is to plug in that value up here and find the value. I'm just going to write that it's f of negative square root of 3 for a value and f of square root of 3. I can see here, square root of 3, 9 minus 18, they're both negative 9. Alright? And those are local mins. Now we can go through and find positive and negative for concavities using the second derivative. Concave down and concave up. Now, before we do that, I said we do the second derivative rule. Second derivative rule says, if the first derivative is 0, and we know the second derivative is positive, that has to be a local min, and that's what checked out here, and here. And the second derivative says, if the first derivative is equal to 0, and the second derivative negative, you have a local max, which happens at 0. So it works out. Concave down is negative second derivative between negative 1 and 1. And concave up from negative infinity to negative square root of 3, and positive square root of 3 to infinity. And again, as we get used to this is going to be a huge help for us when we have to graph functions. Because we can immediately plot points of maxes and mins, and we can use a limit as x goes to infinity to find out what's happening. We know x to the fourth gets really big. So we know rather quickly here that this graph looks something like that, based on its concavity and that. And it has points of inflection at negative 1 and 1. It changes sign. So I have 2 points of inflection. If I plug in 1, I get negative 5. If I plug in negative 1, I get negative 5. We should also notice that this function was even. It was going to mirror across the y-axis immediately. We probably could have done all the work on 1/2 of the graph. Alright. One more. And this one's a little more complicated. There's 2 ways to do it. Most of the time students look at this and they think they want to do the chain or product rule. And that's an okay way to do it. I would not prefer to do it that way. I'm going to show you a shortcut. We'll do the product rule first, just to show how it works out. If you do the product rule of this function, you're going to get square root of the derivative of x is 1, so 1 times x plus 3 plus x times 1/2 of x plus 3 to the half minus 1 is negative half times the derivative of the inside is 1. And you're going to get a product like this, or a product, a sum like this. And we can't really deal with that to find the zeros. So then I'm going to have to find a common denominator. And I'm going to have to do some algebra here. I'm going to have square root of x plus 3 plus x over 2 times the square root of x plus 3. I'm going to see that. I'm going to say, I'm going to have 2 times x plus 3 be the common denominator I need. And I'm going to get 2x plus 6 plus x over 2 times x plus 3. So I'm going to get 3 at 3, and I'm going to factor the 3 at the same time. I can factor this, and I get for lack of a better way of saying it, I have to do a whole lot of work to get to here. And again, I can look at it now and say, okay, the critical points. Where is the derivative 0 or undefined? It's 0 when the numerator is negative 2, right? And it's undefined when the denominator has this be 0, so negative 3. And actually, it's not defined to the left of negative 3. It's undefined to the left of negative 3. So our domain here, changes, And actually, though, our domain of this function is negative 3 and to the right. So it's our derivative here has 2 critical points in the domain, I might have been tempted to do the function this way. I might have been tempted to change x into x squared, the square root of x squared like this. And if I were to bring that in now I can use the product rule, and I could have wrote that as that. Alright? I'm going to get the same answers, and it works out. It's just a matter of what do you find easier. Alright, we don't want to forget we have rules from Algebra 1 and Algebra 2 and Geometry we use in calculus. Alright, so now the derivative of this gets awfully complicated if we're going to do concavity. It's going to be a product rule, or our quotient rule. So, a prime prime of x, is the derivative of the top, which is simply 3 times the bottom minus the top times the derivative of the bottom all over the bottom squared. And now I have to set this equal to 0 and try to find its points of interest to find the chart. Alright, now this is getting to be more difficult. So we're going to have to find a common denominator, and again, this becomes an exercise in algebra. Alright? And if I do that, I'll rewrite the function up top with a little simplification. This is the second derivative now. Alright, I just made the x plus 3 to the negative half power of the square root. And again, you notice I'm going to need a common denominator. That's got to have to be our first step here. So I'm going to get here 6 times x plus 3 minus 3 times x plus 2 all over, and I can bring all this up and write 4 to the x plus 3 to the 3 halves, because again, I can multiply this by this, right? And again, this is algebra 2 stuff, simplification. I get 6x minus 3x, so I get 3x, I get 18 minus 6, I get plus 12. And again, we can quickly see when I get to this little pretty function where this equals 0. Negative 3 on the bottom makes it undefined, but negative 4 on the top, right, makes it 0. So I've worked all this way to find these points. So I'm going to rewrite that second derivative on my previous board, and I'm going to take all 3 derivatives actually and just put them on a new board, because now we got to try to make a table out of all this stuff. All right. So we had the original function, which was x times x plus 3. We just found that the second derivative was 3x plus 12. Or maybe I'll factor it and say 3 times x plus 4 over 4 times x plus 3 to the 3 halves. And we know negative 4 makes it 0, so I'll write that over there as a point of interest. We also knew that our first derivative, if I go back to my previous board down here where you can't see, and write it down up here for you guys to see, was 3 times x plus 2 all over 2 times the square root of x plus 3. And we already said negative 2 and negative 3. Negative 3 is going to be weird because that's the very left of our domain of our function up there. So I'm going to write the negative 3 right at the top so it can't get any bigger. And negative 4 is outside the domain now that I say it, so I don't have to worry about it. So there is going to be no concavity change. It'll be one way or the other. And we do have negative 2 up here. F of x, f prime of x, f prime prime of x. That's actually for notes. And again, negative 2 made the first derivative 0. So if I look at the second derivative right now, I might just plug negative 2 in. Let's use the second derivative rule and see how fast we can go. If I plug in negative 2 into this function up here, I get 1 on the bottom. So the bottom's positive. I plug negative 2, the top's positive. This is a positive. So again, the second derivative rule says if the first derivative is 0 and it's positive, concave up, it's a minimum. This is a local min by the second derivative rule. And we also know the function's concave up. If it's a minimum, it should go from positive to negative. So the first derivative should be positive to negative. We can check ourselves here. So if I plug in 0, I get a positive answer up there. That's great. If I plug in a number over here, I get, let's see, negative, oh, it's negative. I gotta check negatives. I'm sorry. If I plug in negative 2.5, it's positive. Oh, it's negative. Sorry. It's negative. It should be negative because I forgot. I gotta use negative 2.5. Slowed down there because it wasn't going to work. If I plug in a big positive number, that's what I was thinking here. It's positive. So this is a local min. And there is no points of inflection. And it's concave up everywhere in its domain. So its derivative, it's decreasing from And again, I gotta stress, I probably should write this. The domain of this function is -3 to infinity. You gotta catch that the radical, the root function, controls it. So it's decreasing from -3 to -2. It's increasing from -2 to infinity. There is a local min at -2, which is a value of -2. If you plug it in, you'll see that that's what it works out to be. And finally, it is concave up through its whole function with no points of inflection, because there's no change in the second derivative. Again, these problems are complicated. They take practice. Keep grinding at it, finding those critical points, making tables and charts that you can read.